Okay, good morning. I'm just summarizing here what we talked about last time. We talked about reinforcement learning, the setup where you have an agent and an environment. The environment or the system is at any one time in a particular state out of a finite number of states. Typically we deal with a finite discrete number of states, but you can generalize it to infinite or even a continuous state space. The agent at any time has a choice of actions. They might be specific to the state, but we can generalize it and say there's overall a set of actions that they can take. They know what state they're in, usually. They take an action. That action results in some change in the environment, transition to a different state at time t+1. Again, we assume time is discrete. Again, you can think of generalizations where time is continuous. Then you have to make continuous decisions. It results in a change to a different state and a reward being given. And our goal is to find a policy, namely a rule for choosing actions based on the state we're in, that will maximize our cumulative future rewards. And we discussed the need to discount future rewards for a variety of reasons. If we discount them, it gives us a finite expected sum of these rewards, and now we can consider all possible policies. What makes a policy good or not is, of course, these two functions: the transfer function, or the next state function, that takes as input the current state and the action and tells you what state you're going to be in, and the reward function takes as input the same thing and tells you what the current reward is, the immediate reward is. Either one of these two functions could be deterministic or not deterministic. Either one of these two functions could be known to the agent or to the learner or not known. When these functions are not deterministic, it doesn't complicate learning too much. It changes the definition of what you learn. Instead of having to maximize the cumulative future rewards, you maximize the expected value of the cumulative future rewards, because the cumulative future rewards under any given policy is going to be non-deterministic. It's going to be a random variable as opposed to a fully deterministic calculable value. Okay? So that's a small change from here to here. That's true if the reward function is non-deterministic, or if the next move or next state function is non-deterministic. Either or both would require the move to an expectation rather than exact calculation. We define the optimal policy. Pi star is the one that maximizes this thing, and then we also define the value of a given state as the value of a given state under a given policy is the expected total future discounted rewards you're going to get if you start from that state and follow that policy. With the understanding again that if it's a non-deterministic world, we're talking about the expectation of the total reward rather than the actual total reward. If I take not just any policy but the optimal policy, I get the optimal value of the state. So that's all in theory. Now the question is, how do we learn the optimal policy? And we discussed the fact that this V function, the intrinsic value of every state, has an interesting recursive relationship. And we could use that to bootstrap our learning. So first, intuitively, what is this V value? It's the value of being in any one of these states, if assuming optimal management from there on. So again, comparing it to the business world, it's the value of being able to hold on to any particular position, either a portfolio of financial assets or a company or anything. It's something that has value because it will give you future benefits, dividends or profits. But it's up to you to. You're going to assume that it's going to be done under optimal management, and it's an uncertain world out there, so it may be just an expectation over your reward. But nonetheless, it is the value of being in any one particular state. And we talked about the possibility of building a table of V values and then incrementally updating it. This would work well if you could do everything by simulation. Namely, if you could, if the transfer function and the reward function are known in advance, and let's assume for simplicity that they are deterministic, although it will work even if they're not, then you could do everything on paper without committing. You could just simulate the development of the system, start from a certain state and say, okay, let's say I take this action, I move to this state, and I gave you this relationship between V of state that you visit at time t plus 1 and V of a state that you came from. So you can choose between taking any one of the actions, so you call it AI, all actions that are available to you. I'm having a hard time separating my gamma from R. Is this a good gamma? I don't know. This is gamma, this is R. This time the future value, oopsie, of state t plus 1. Let me write it a little better, I'm sorry. I'm trying to put some bound on the optimal value of the state that we ended up transitioning to, and therefore we're in a t plus 1. And it's related to no, this is no good, so let me rederive it. There's a state 1 here and there's a state 2 here. It has a value. And the only thing I observed was that if I can take action that would take me from here to here and give me a reward along that time, then it must be the case that the value of this place is at least the value of the reward plus the discounted value of S2 in a deterministic world where I know I will get there. So that was the underlying observation, is that the value of every state is the maximum of all the options that are available to me. I can either take this action, get this reward, and go to that value, or take this action, get this reward, and go to that value. Okay? So this gives me a recursive relationship which I could use to iteratively refine my estimate of V. I can only do that if I have a known, and in this example, deterministic relationship, the transition and the reward. What can I do when it's either not known or non-deterministic? Especially when it's not known. When I don't know what outcome my actions will give me. I don't know the value of these two functions. I don't know what reward I'll get, and I don't know what state I'm going to end up in. I have to experiment. I have to actually use the system. I cannot do it on paper. So what I'm going to do is I'm going to use this intuition about this relationship, but I can no longer explicitly do a maximization over all possible states, S3, S4, S5. I can no longer calculate all of them and choose the largest one. I just need to choose one action and see and take it and see what happens, what reward I get, what state I end up in. And that would still could be used to improve my estimate of V, but not as efficiently as if I were able to do it on paper and look at all of them. Because intuitively thinking, you would need to be back in this state k times if you have k actions, and try all different k ones in order to get as much information as you would get by simulation and looking at all k. Effectively, the simulation is, virtually taking all of these steps at the same time. So if I don't know these functions and I have to actually try it in the real world, every step I learn very little. I just learn about what happens if you're in this state and take this action. So that's what I'm going to do. And to do that, I'm going to define a precursor to V and call it Q. The difference between V and Q is that V captures the value of a given state. Okay, it's a function only of the state. It captured everything about the state, including all the possible actions I can take. Q is a precursor to it. Q is specific not only to a state, but to a state and an action. So Q is the value of being in a state and taking that action. Of course, V and Q are closely related. You can express V in terms of Q and Q in terms of V, and we're going to do that. I'm trying to give you the intuition first. You can think of Q as a precursor to V, to the true value function. It is, unlike V, which depends only on the state, it is a function of the pair, state and action. And we're going to need that whenever the world is not known to us, because we're going to just explore. We're going to try. I'm in this state, I'm taking this action, let's see what reward I get, let's see what state I'm getting into, and I'm going to use that to define a iterative refinement of estimated Q values. So I'm going to start with some Q values, which are going to be all 0, and I'm going to iteratively refine them and improve them, actually increase their value. So here's the Q function. It's a function of the state and the action, and it's defined as the reward you get from being in that state and taking this action, plus a discounted value of the optimal value of the next state you end up in. State action. So we were in state A, we took action, state S took action A, the transfer function took us to a new state. It has some intrinsic value, which we don't know what it is, according to the optimal policy. It has to be discounted because it's one step away. Add to it the reward we currently got, and this is the value of our Q function. Now, the interesting thing is that we can now define the optimal policy with regard to given a certain state S in terms of the Q function. First of all, it's the one that maximizes over all possible actions future rewards, which is SMA plus gamma times future value of whatever state we're going to be in next time. Convince yourself that this is correct. The definition of an optimal policy is one that maximizes current reward plus discounted future rewards. But this is exactly as we defined the Q function. So this is the same as maximizing over all state A the Q function. So all I did was I took this part and gave it a name, Q function, and then I argue that if we knew the Q function, this gives us the rule what to do. So if somebody handed you the correct Q function, then you would know what action to take in every state. Just take this action. Calculate the value of Q for all possible actions in that state and take the maximal one.
In your Q function, is it R parentheses S there, or is that the gamma?
I'm sorry, it's R. So I should learn to write nicer R's. Yeah, I don't even know how to do that. I can use capital, but it's kind of different from the book. So I'll put a little star here to say that this is a variable in its own right. It's not a function. I'm sorry. So R? No, I don't know how to write R. R? This is a gamma. Alright, I'll just make this R. Maybe somebody will teach me after class. I'm sorry. Okay, so all I did here was define what Q was mathematically and showed you that if you knew Q, that gives you the rule for how to behave. What's the optimal decision? And now, I'll give you a relationship between V and Q. V star of any state S can be written as the maximum over all possible actions A prime of Q star A prime. The value of a state is the maximum value of any action you can take from that state. So the way to think about it is V is the intrinsic value of a state, and Q is the value of a state assuming you're going to take a particular action A. Different actions that you take will have different values. But the intrinsic value of the state is the maximum value you can get any action in that state. So you can express V in terms of Q, and you can also express Q in terms of V. Which means you can create a recursive relationship between V and V or Q and Q. Okay, because you can say V in terms of Q and Q in terms of V. You do it twice. So we're going to do that. Q of state T taking action T is defined first as the reward you get from being in state T and taking action T plus gamma times the intrinsic value of the successor state to ST AT. So far it's just a definition I copied from there, and I'm going to take this and plug in this dependence. This gives me reward function of S sub t A sub t plus gamma times maximum over all possible actions A prime of the Q function applied to the successive state. Call it S prime and A prime. It's important that these are different in these states. I call this ST and AT. Maybe I should call this ST plus 1 and AT plus 1. Well, this is not AT plus 1. This is considering all possible A, so I'll still keep it A prime. But it is ST plus 1 because once I decided to take some action A sub t, I'm going to end up in some state. I don't have control over it. The important thing is that I now have a recursive relationship over Q, no longer involving V. So suppose I have some estimate for Q. I'll put a twiddle on it for the estimate. I can now refine my estimate for this particular entry in the Q table based on all these values. So imagine I have a tentative table of Q values. Here are the S's, S1 through Sn. Here are the actions, A1 through AM. These are the Q values. Now I'm in a particular state. I'm going to take some action. I'm free to take any action I want. I'm going to take some action. And if I'm in this state here, Si, and I take action Aj, I'm going to update my value of Q for this position, QSI Aj. And the update is going to be, I will actually take this action. I have to take it because I don't know otherwise what would happen. I have to take it in the real world. Once I take this action, I observe some reward. And I now know what my next state is. I get back my next state. That next state is going to be called S prime or ST plus 1. Now that I know what that state is, I can consult the Q table for that successor state and all possible actions that follow it. I don't actually take all these actions. I just consider all of them. So if my successor state is S prime, then I consider all these values here, take the maximum over them. Because I tell myself, if I took this action and I ended up in this state, now I could take, the next action could come from anywhere here, and I'm assuming now that this is correct. I know it's not the correct table, but I'm assuming now temporally this is the correct table. This is my tentative values. So I'll take the maximum value, discount it appropriately, add to it the current reward that I got, and this would be my refined estimate of this position. Question? Yeah.
So it sounds like this is for unknown but deterministic?
Correct.
Okay. And it sounds like, I don't think it would stabilize if you had non-deterministic.
This is a wonderful comment. What would happen in non-deterministic? Don't let me forget it.
Okay.
I'll get there. This is exactly right. This is for unknown but deterministic world. The important thing is it's unknown. Because it's unknown, we actually have to take the steps and observe what happens. Observe what reward we got and what state we ended up in. And it's not very efficient because we have to do it many times. When we were here in this state, we decided to take this action. But the next time we're in this state, we might want to take a different action because we might learn something else from it. Now, if the world was known, as I mentioned before, we didn't have to take any steps. We could stay home and just calculate what would happen if we took all these steps. But since that's not the case, we actually have to act in the real world, which might have some costs to it. Anyway, we have a recursive relationship on re-estimating Q, and this algorithm is called Q-learning. Now, Q-learning has wonderful properties, theoretical properties. You can show that if you start with Q table of being 0, every entry is 0, and the rewards are always non-negative, then the Q value would only grow, which is kind of intuitively understand. At least in the beginning, if they're 0, what you're doing is you replace each Q value with some non-negative reward plus the maximum of some other Q values. So in the beginning it's clear that it's going to go up, but you can show later that it's only going to go up, and further, it will never go above the true Q value. Even stronger than that, you can show that it will asymptotically reach the correct Q value. So the algorithm is guaranteed, under some conditions, to converge on the correct Q values. That's a wonderful learning result. It's an algorithm that's guaranteed to learn the right thing. The right thing, and now with no apologies. It is the right thing. It is the optimal value, and it can be used to make optimal decisions and all of that. Two twists. One twist is, what are the conditions under which it's guaranteed to converge? The conditions are that every state and every action must be visited infinitely often, which, to those of you who didn't take calculus, means that if you continue that for an indefinite amount of time, none of them get left out. Everyone gets revisited again and again and again. So in practice, what it means is that all states and all actions out of states must be visited many times. Not just once, but many, many times. So that's, if you have a table, if you have n states and m actions, there's n times m state action pairs must be visited again and again and again. The second caveat is related. It'll take forever for it to converge. not realistic for any reasonable size problems. 3 states and 4 actions can take a long, long, long time. 100 states and 17 actions, forget it.
The first constraint, that's just saying that if you draw the state action graph, that it has to be strongly connected? Or is that the
No. So actually that needs to be refined. So when I said that every state needs to be visited, if you restrict yourself to one chain of learning, namely you start from some state and you take actions, and wherever it takes you, then in order to guarantee that you will visit every state and every action, you need to have some kind of condition on the connectivity. It has to be, what's the term for it from Markov chains? What's the term for a chain that you're guaranteed to visit every state? Ergodic, thank you. Just blanked out on the name. It has to be ergodic, that would be a requirement. But it turns out you don't have to use a single chain to learn. You can start from, depending on the setup you're in, you can start from some state and go for a while. Take an action, go wherever it takes you, take another action, go wherever it takes you, and keep learning. And then at some point you can decide, let's get out of this state and let's start again from this state. Often you can do it in the real world. If you're doing robot learning, and the robot has to find a way to the socket to charge themselves, you can place the robot here, that's one state, and let it move around a little, and then you can stop and pick it up and put it somewhere else, or put it back where it was, right? So many times you're in a situation where you can choose to reposition yourself in a different state. You can even take it to an extreme. You can reposition yourself after every step. So you can choose where in this table, which entry in the table you're going to fill next. You can say, I want to be now in this state, and I'm going to try taking this action. Take this action, do one update of this formula, one update of this particular cell, then take the robot or whatever unit you are, now I want to be in this state and do this action. So you can, it's up to you, in many world situations, to fill this table in any way you want. In other situations where you don't have control over, you cannot restart your system. You must start wherever you are and follow it wherever it takes you, and then you have to hope for ergodicity and for visiting all these states as often as you need to. Questions, please.
So where does the generalization part come in? So each time we are in a different environment, do we have to, like, unless we can map the states, we have to learn all over again?
Every time we're in a different environment. When you say a different environment, do you mean a different world where the reward function and the transit function are different? Or do you mean...
I mean, if it's a robot, then maybe a different street or a different terrain. Or
Yeah. So that's a very good point. If your problem setup is such that if you're in this room, you have a certain number of states and rewards and transitions, and it's different than what the rewards and transitions are going to be in the street, then it's a different learning problem. It's up to you as a modeler to try to abstract things away and find commonalities so that you can learn something that would be useful in all of them. But you're right, it's hard to do.
But yeah, it's a robot that assists somebody in a certain house or a certain location, then it will be a consistent environment. So that might...
Yes, and often in the real world, something like robot learning, you have so many states. Often you think about it as continuous states. But at least you have thousands of states that it becomes computationally infeasible to use reinforcement learning. You have to start thinking of shortcuts, and so not reinforcement learning, Q learning. So Q learning is beautiful, but just not very, very realistic, not very practical. And now you have to start making approximations and shortcuts and heuristics and so forth. Okay, so now let's deal with the situation where it's non-deterministic. And you were pointing out that something bad is going to happen if you follow it when it's not deterministic. It's not going to converge. That's exactly right. I'm sorry, I forgot to mention one thing, so let's put the non-deterministic on hold, and I just want to show you the Q table for that small world that we've discussed last time, and then come back to the non-determinism. So if you remember, we had a world with 6 states only, and it had a very limited number of actions. It was basically up, down, right, left, and even those were not all available in all states. You could only go to neighboring states, and there was one goal state, and you got a reward when you moved into it, and that's it, and then you could move out. So it's a very artificial world that's set up to teach you to get to the goal state as quickly as possible. Where did I put my pointer? Here's the reward function. Here's one optimal policy. If you're here, make a right. If you're here, make a right. If you're here, go up, and so forth. Here are the optimal values, the V stars, based on that optimal policy. You see that being in a goal state has a value of 0, because then you can never get your bonus. Being here or here 1 step away has the most value. This is being 2 steps away, and this is being 3 steps away. The discount factor is 0.9 for every step. This table was annotated with the Q values, the correct Q values. This does not involve any learning. We're fully analyzing this world, and we know all the functions, everything is known and deterministic, so we can calculate what the Q values are. For example, Q values, first of all, are no longer associated with a particular state. They're associated with a state and an action. So we write them above the arrows. So this is the Q value associated with being in this state and taking this action. And not surprisingly, this value is 100. But if you're in this state and for some reason you choose to take this action, your value is much lower. It's 81, because you now put yourself 2 steps away from here. If you took this action also, your value is 81. If you're here, the Q value for going up or to the right is 90, because both of them will get you to the goal in 1 step. If you choose to go away, your Q value goes down, because now you put yourself 3 steps away. Now you can look at this, and I encourage you to do it at home when you go over this material, and compare it to the recursive relationship we had. The relationship between Q and V. V for a state is defined as the maximum of all the Q's emerging out of that state. So V here is the maximum over all the arrows coming out. And similarly, Q can be defined in terms of V. Q of a state is the immediate reward plus a discount value of the value of the successive states. In our case, the immediate reward is almost always 0, except if you go into the goal. So for small worlds, it should be possible for you to fully calculate what the V value, what the Q value is, convince yourself the recursive relationship works. And then this kind of world, if you didn't know the Q values, you started with the Q values of 0, and you transitioned in it, you will learn the Q value, you will converge to the right answer fairly quickly.
Actually, you get stuck in the goal.
But then you have to restart. Okay. That's exactly the point. This is exactly what we talked about before. You will get stuck in the goal, and then you will need to restart. So where do you restart? Well, if you can choose, you restart in different places at different times. You have to make sure that you visit not only every state equally often, but also every state that you visit, you have to try all possible actions. So this leads us to the next discussion, which is the algorithm, the Q-learning algorithm, does not specify for you which action to take when. Let's even say that you do one chain. You never get stuck. You just start and you follow it. And as you follow it, you update the Q values in the table. At any point you're at a given state, you have to decide on an action to take. There are many ways to choose which action to take. The only requirement is that in the long term you should try all of them. But that still gives you a tremendous amount of freedom. You can go through them sequentially, like keep a list of which ones you tried and just cycle through all of them. You could favor some over others. Suppose you've gone through your training now for a while, and your Q function is pretty good now. It still hasn't converged fully, but it's a very reasonably accurate approximation of the real Q value. In that case, when you're in a given state, you have a pretty good idea of which is the best action to take in terms of maximizing your future rewards. Right? So if you are now told, okay, time to stop learning, now we're only going to test you, you would not randomly choose a state or an action or cycle through the action. So you will go for the one that maximizes, that gives you the best future benefits based on your current Q estimate. Right? That's if you were told, no more learning, it's time to start reaping benefits. What if you were told the opposite? Say, take your time, you can train for forever, I want you to find the best possible policy. I know your cue is pretty good, but I want it to be perfect. In that case, you will cycle through all the actions to try to refine the cue estimate for all the actions, right? In the real world, we're somewhere in between these two. If you train on the job, you are given some leeway to try different things because that's how you learn, but at the same time you're expected to also generate some benefit. So this is the exploration versus exploitation concept that we discussed last time. And there's absolutely an inherent trade-off between the two. I think we talked about finding the example of finding your best driving path to go from home to your work, right? So think about a cue table, and every intersection you're at is a state, and the action is to make a right, left, or go straight. Now, you may experiment with many different ways of getting to work, and suppose you're trying to optimize your driving time, minimize your driving time. After experimenting for quite a while, your cue table is pretty good, and the path that you will follow will be pretty close to the optimal one. Maybe not the optimal one, but pretty close. And now you're facing a dilemma. You're not doing it for other people, you're doing it for yourself, but you still have a dilemma in that on one hand, you want to start using the shortest possible paths. You're tired of training, you're tired of getting lost in small streets and so forth. You want to start getting to work on time. On the other hand, you want to improve you want to experiment and maybe find a faster way of getting there. Often if you're married, or if you drive with somebody else, there's the one person who wants to experiment with finding a better way of doing things, and there's the other person who wants to say, let's just not take any risks and get there. I don't know if you're familiar with that debate. But it basically represents different trade-offs between exploration and exploitation. Shai?
Don't you really find our delta in that way?
Don't you find what?
Don't you find our delta that way? What you're actually doing is finding our delta. You're going over all stages. So, if you do find our delta, then it's the regular.
That's a good point. So if R and delta are deterministic, and if you visited every state and took every action, then now they're known to you, right? Now you know, basically by trial and error, you know the two functions. What for every state and every action, what reward you get and what state you end up in, right? And now you no longer have to do it in the street; you can do it on paper. You still need to go through that cue learning, or you could do it recursively directly on the V. But you could specifically do cue learning, but without having to actually drive through the streets. You can do it by simulation, yes, if they're deterministic. Quite true. Okay, now we're ready to discuss what happens when they're not deterministic. And indeed, it's true that if you're not careful, you will not converge. And the reason you will not converge is that, well, there are many ways of trying to explain it. The way I like to think about it is that a non-deterministic world can be thought of as many different deterministic worlds that keep changing. But the world is deterministic, it keeps changing. And if it keeps changing, then the optimal decision keeps changing. And in the optimal decision for a non-deterministic world is sort of an average over all possible worlds. But this step of learning takes too seriously what happened just now. It tries to adjust your decision based on the world the way it was today. And if the world keeps changing, then you can imagine it might constantly tell you, no, do it this way, do it that way, do it this way, do it that way. Any suggestions what to do about it? How do you learn in a non-deterministic world? Then?
You have memory. You get some sort of memory for states. If you remember how many times you've been there and took that action, how many times you've been there and took that action, it's average. You take the maximum line because
Okay, so you keep track, you have memory, you keep track of every time you were in this state and took this action, what were all the rewards that you've experienced, and what were all the states you transitioned into, and you build some kind of estimate of the distribution of rewards and distribution of transitions, and then you make your decisions based on that. You could do that. Some problem with that is that you may need a lot of times in each one to derive reasonable estimates, and then to derive an optimal decision from that would require some more computation. Namely, suppose you knew the full non-deterministic function, calculating the expectations would still be an open problem. You could actually use Q-learning in a non-deterministic world as long as you make one small change, and the small change is to not allow every step to move you too much. So imagine that you're allowing every step that you take, every Q-learning update, to move you an amount that keeps going down with time. So it's multiplied by some factor that keeps shrinking. As long as it keeps shrinking towards 0, that means you will converge, because the changes you make go to 0. At the same time, you don't want it to go to 0 too fast, because you want the cumulative effect to not be bounded. If the cumulative effect is bounded, then there's only so much you can learn. But if the cumulative effect is not bounded, then you will, over a long period of time, move to wherever you need to move to. This is not a mathematical proof, it's hand-waving. But if you remember something from your calculus class, you can think of a way of converging towards 0, such that every term goes towards 0, but the sum doesn't go to 0. Do you remember that? From, I don't know, high school or... Do you know this sum? 1 over k to the alpha. It goes from 1 to infinity. Does this converge or not? Cash in you? Yeah. Yes? So let's try sum over 1 over k squared. So alpha is 2. Does this converge? Okay, 1 over k to the third. Does this converge? 1 over k. Does this converge? No. Okay, so what's the condition? Do you remember? Alpha is to be greater than 1. Alpha is greater than 1 converges. Alpha of 1 and certainly less does not converge. It's just a little calculus trick. So let me show you the formula that was worked out for the non-deterministic case. I was trying to give you at least my explanation on mathematical intuition of why it works. So this is a non-deterministic world now, and Q-learning, the original Q-learning formula which I have there, is the next value of Qn for this particular cell is defined as just this part, the reward you currently get, and the maximum over the Q value for the successor state over all possible actions. The change is to smooth, no longer take the new estimate at face value, but to combine it with the past estimate. So don't replace that cell content, but do a weighted combination of the existing cell content with the replacement value. This is the replacement value, this is the old cell content. And here are the weights. It's alpha n weight and 1 minus alpha n. And alpha n is an amount that goes down to 0, based on the number of visits to that particular state and taking that action. And the way it goes down is exactly as I predicted before. It's with the alpha, the speed with which it goes down is exponent of alpha equal 1, which is just enough to go down to 0 and therefore guarantee convergence, because the amount of changes, the absolute amount of the change goes towards 0, so you'll converge. But it's not too fast, so that the cumulative effect can take you anywhere you need to go. This is not explained in the book, but if you're wondering where people come up with these formulas, at least that's my intuition for why this formula and nothing else. So my suspicion is that if you put squared here, it would not work. Converge too fast. Questions? Okay, we have about a lecture and a half left, and we're going to do a potpourri of things. We're going to talk about a little bit about different areas. I should use the opportunity to ask you to fill the faculty course evaluation, which is now online. It is very useful for the university. It is certainly very useful for me. Whatever positive, negative comments you might have, I would really like to hear. As you know by now, I definitely have my way of teaching. Mostly I try to avoid slides and avoid computer projection, and I'd like to hear what people think about it, whether positive or negative, or any other aspect. So by all means, please try to take a few minutes and fill the FCEs. It's important. It's like voting in a democracy. So that's one announcement. The second announcement is we have a final exam scheduled. There was a brief time when the official room assignment was different than it is now. Do you remember, Anjan, what the correct room assignment is now? They gave us 2 rooms, and I really didn't like that, so I moved us into a single room. It's in Margaret Morrison. If you don't know the rooms there, I urge you to go ahead of time so that you don't lose time in the morning of. I should do the same thing because I don't know where it is. It's the first time they put me there. Do check now online. Both you can check on the course web page as well as in the official CMU registrar website where the exam is going to be. It's 3 hours, which means we can cover a lot more than we could in the midterm. What I intend to do is to try to use a lot of relatively small questions. All the material in the exam is fair game. All the material in the course is fair game. I think, generally speaking, I will maybe place more emphasis on the second part of the course since we haven't been tested on it yet. But we can certainly go back to the first half, any part of it. The general rules are the same as in the midterm. You can bring one double-sided sheet of paper, 8.5 by 11. Summarize on it whenever you need to summarize. Any questions? Please. Putting up practice?
A practice final, like a final?
I don't think so. If you're looking for the kind of questions, the midterm is an indication of the kind of question. If you're looking for things to practice, the questions in the book are pretty good. Not those that require programming, and not those that require real proofs. So these are 2 things I try to not put in an exam, like calculus style proof when you have to go through a long thing to prove something is greater than something else. I try to avoid that. Certainly anything that involves programming, I try to stick to conceptual. What do you think, this is bigger than this or smaller than this? Explain in 1 or 2 sentences, kind of thing. The material from the last few weeks is very hard to give you an assignment and have enough time to grade it and give you meaningful feedback. So what I usually do is we have one more assignment which is not going to be graded. It's strictly for you to practice, and it's made of sort of the kind of questions that could be in the final. And it will go up. Could go up today, I suppose. It's not any different than last year. And we will put up the solutions at least a few days before the exam. So you can. We could put out the solutions now, but I would like to encourage you to not look at the solutions. Do it, write it down. It's strictly for you. So it's to give you the practice, but without any delay of grading, and it's not strictly required. Now I know you're probably under a lot of stress now with other exams and so forth, but it is a very good way to practice the material and to practice for the exam. So think about it as part of preparation for the exam. Any other questions? Okay, so I want to tell you about two techniques that were invented about 5 to 10 years ago, neither of which are primary techniques. They're both secondary techniques. They take an existing machine learning technique and they improve on it. One is called bagging, the other one is called boosting. So I'll start with bagging. It's pretty simple. Suppose you try to learn a decision tree. You have 1,000 data points. The way we learn how to do it is you take the 1,000 data points and you feed them into the decision tree building algorithm. And maybe you save 100 or 200 on the side for testing or for deciding when to stop growing the tree or any of these things. And suppose you have separate data for validation and testing. For training, you take your training data points and you throw them into the algorithm. Now, we talked a little bit about, in statistical estimation, we talked about bias and variance. Remember that? Bias is a systematic tendency to overshoot or undershoot. Variance is the tendency to generally fluctuate depending on the training data that you have. When you build a decision tree, decision trees have notoriously wide variances. That is, they're very sensitive to fluctuations in the data. So if you think about it, when you make a decision on what node to split, the decision could be very close. And if you consider multiple attributes, two of them might be really close, and depending on how much data you happen to have and what particular data you got today, you might split on one of them or the other. And once you make that splitting decision, the future looks very different. Right? Once you decided on a particular attribute, the rest of the tree would look very different than if you decided on the other attribute. So decision trees have quite high variance. So the idea behind bagging is to try to reduce the variance of something like decision trees by doing the following thing. The procedure is quite general. It's not just for decision trees. You take your whole data, and instead of training your decision tree on the whole data, you train it on some subset of it. So you randomly choose some subset of, let's say, 70% of the data. And you train your decision tree on it. And then you throw the data back into the pool, and then you randomly select a different subset of 70%. And you train a different decision tree on that subset. You throw it back, you take another 70%. So you keep sampling from your training set. That notion of sampling from a finite set is called bootstrap. The bootstrap method actually has been known and used in statistical estimation for many years. There are actually amazing things you can do with bootstrap. You're basically simulating the distribution from which your data came. Of course, it's not the same. sampling from a fixed 1,000 data points is not the same as sampling from your true distribution. But many aspects of the sampling are the same. Many statistical properties of sampling from a finite distribution is very similar to sampling from the distribution from which that finite distribution came. So that's called bootstrap. And you do a bootstrap and you train many, many trees. And then, as you probably guess, you average their predictions. If their predictions are classification, you take the majority vote. If their prediction is regression, you take their average. You somehow average the behavior of all the trees. And now the interesting thing is that the average decision that you get this way is systematically better than the decision you get from if you took the whole data and built one tree. By systematically better, of course I cannot guarantee it would always be better. That depends on your data. But it has a lower average error rate if the experiment is repeated many, many times with many different data sets. Why? I already gave you the answer. Bagging is a form of reducing variance. So any technique, any machine learning technique that you suspect has too much variance, you could counter that variance by doing a bootstrap, training many, many different classifiers of the same type and averaging their result. The theory actually goes beyond that, and it can actually give you optimal values. Turns out that 68% under some conditions, 68% is very close to optimal. Why? Well, there's a certain balance here between, if you took 100%, then you're not reducing the variance. You're always getting the same training set. If you go to the other extreme and take 1%, maybe you don't have enough data. I don't know. I just know that under some conditions, 68% was calculated to be optimal. And of course, how many times you do it is also important. What you're paying here is increased computing time, because you have to train, in this case, a decision tree many, many times, maybe 1,000 times. So that's bagging. Another sort of secondary technique that comes on top of this one, which was invented around the same time, but actually was taken a lot further, is called boosting. By the way, there are slides describing all of this online. I'm just giving you the intuitive lecture. The idea behind boosting applies to classification. And the idea behind boosting is that first you do the best job you can with a standard classifier, and then you observe the errors that you made, and you try to change your classifier to be more sensitive to the points that you got wrong. So most other global techniques try to create a better classifier, and by better you might mean that takes the points that were put in the right side of the classification line and push them further out. But if all you care about is your classification rate, or your error rate of classification, once you got a point to the right side of the decision boundary, you don't care anymore what happens to it. You want to pay attention more to the points that are on the wrong side, or a variation that is to say, if a point is very close to the decision boundary, you want to push it out. But once it's further enough, you don't care if it's 1 kilometer away or 100,000 kilometers away. It's far enough away. So these are actually two slightly different ideas that they lead to two different general techniques. One having to do with focusing on mistakes that you made and modifying your algorithm or modifying your classification to get rid of these mistakes. The other one has to do with maximizing the margin of error. If you think of here's your decision boundary, what you want is to have a margin on either side. It's not enough that all the pluses would be on one side and all the minuses would be on the other side. you want the pluses and minuses to be as far from the actual decision boundary as possible. If all you had was these 3 data points and these 3 data points, this is a good decision boundary, but so is this one. Right? They both divide. But we all have an intuitive understanding that this one is a better one. Because you don't want a decision boundary that passes right near your points. You'd rather your points were, quite a distance from it. So based on this intuition, we would predict that, say, a point here is negative rather than positive point, because we believe this decision boundary is better than this one. So this leads to a whole theory of classification called maximum margin classifications, which is conceptually related to boosting but not quite the same. In boosting we care mostly about emphasizing or focusing on the points that we got wrong. Now, how can you emphasize or build up the points how can you focus on the points that you got wrong in a very generic way, in a very general way, without committing to a particular learning algorithm? Well, here's a clever way of doing it. Suppose you reweigh your training data and then run the same algorithm again. Remember, we're dealing now with a secondary method, not with a primary learning algorithm, but with a method that takes any learning algorithm and improves on it. So suppose you have some learning algorithm, you don't even care what it is, it's a black box. You throw in data, training data, out come a classifier that does a pretty good job on the data. It doesn't have to be a great job, it could be 60% accuracy, 80% accuracy, 90% accuracy, whatever. More than 50% for a binary classification. You can now, this is an amazing discovery, you can now create an incredibly accurate classifier by just using this black box again and again and again. And the way you do it is you use it once with your original data, you got the classifier out, you see how well it performs on your training data. It got a few things wrong. You take the things that it did wrong and you multiply them. You pretend that they are present in the training data more than they really are, in multiple copies. So you boost their presence in your training data. Another way of thinking about it is you take the others that you got right and you deflate their presence in the training data. So you can think of every data point as being present in training data once or twice or 3 times or a fractional number of times. So you take your black box, you apply it once, you classify each data point about whether you got it right or wrong. Those that you got right, you shrink. Those that you got wrong, you boost up. And now you take your reweighted training data and throw it back into the same black box. And now it does maybe a little better. And now you take the outcome of that and again you boost up or down depending on whether it got it right or wrong. And you repeat it again and again and again, and at the end you combine all the classifiers from all these steps. And lo and behold, the combined result is much more accurate than the original one-shot black box. The amazing thing about it is that this works regardless of what your black box is. As long as your black box has the property that anything you put in, out comes a classifier that's more than 50% correct. I'm talking about binary classification, that's more than random correct. More bounded away from 50%, so it has to be 50 plus epsilon. You fix the epsilon. So any weak learner, any weak learning algorithm that learns only 51% accuracy of binary classification can be used repeatedly, can be boosted, and then combined together to give a very accurate final combined outcome. Let me show you a pictorial view of what's happening. It's quite nice. Okay, so here's our example. It's a binary classification problem, and as you see, it's a very difficult classification problem. It's not clear to see what the separating line is, and we're going to try to learn it with a very weak learner, a learner that can only put horizontal or vertical lines. Okay, clearly that kind of a learner cannot get very accurate results here, cannot accurately